Hello, everyone, and welcome to another wonderful day of chemistry. We're going to continue our conversation about entropy. Specifically, we're going to go from the entropies of individual substances to the entropies of reactions. So as we said previously, we can model how entropies change using the fact that they're a state function, which means we can calculate the entropies of reaction in a very similar way as to how we did it for enthalpy. All you need to know is the entropy of your products and your reactants. The difference in between these two numbers should simply give you an entropy of reaction. So let's go ahead and take a look at last time. We were looking at the processes of fusion and vaporization. So if I want to find the entropy of fusion, all I need to do is find a value for the entropy of a liquid and the solid and just take the difference. Similarly, you can do the same thing for vaporization, where it's just gas minus liquid. Now, one of the cool things that's worth making note of with entropies of these phase changes is that in general, as we saw, the difference in between a gas and a liquid is much greater than a liquid and a solid. Because when push comes to shove, a liquid isn't that much more disordered than a solid. However, you literally can't get more disordered than a gas. So as a result, we tend to find entropies of vaporization being much greater than entropies of fusion. However, turns out phase changes aren't really chemical reactions, they're just changes in IMFs. So let's go ahead and take a look at how we can find the entropy for an actual reaction. So let's go with one of our classics, combustion. And let's keep it simple and look at burning methane. So in this case, I combine methane with oxygen and a little bit of heat, and I'll generate carbon dioxide and water. So should be fairly straightforward. But remember, when we're calculating our entropies, you need to account for stoichiometry. So we're going to do products minus reactants. In this case, we're going to have to add together CO2 and water, remembering that we have two waters, so we have to double its entropy. The annoying size and extensivity of entropy. Then we can go ahead and subtract out our reactants, methane, and again, two oxygen atoms. And then simply using the difference of these, we can go ahead and determine the entropy of any reaction, in this case, a combustion. Now, one of the things I do want to make note of is that reactions that tend to generate more gas phase products will tend to have much higher entropies of reaction. So let's go ahead and take a look at what we'd expect of this reaction. So it's worth noting that I have on my reactant side three different gas phase species, methane and two oxygens. On the product side, I've got CO2 and liquid water. Well, we know the entropies of liquids tend to be much lower. So in general, we would expect this process to actually have a decrease in entropy. So the entropy of this process would be negative, and that actually turns out to be the case. It may seem weird, but when you're burning methane, you actually tend to order the universe a little bit more. So, so one of the things that is worth noting is that this is only really the case for burning small molecules, so those found in natural gas, methane and ethane. By the time you get to heavier and heavier molecules, then the thing we're burning is no longer a gas, and we end up producing a lot more CO2 for good or for ill. And this is one of the reasons why gasoline and oil, when they're burned, tend to have positive entropies of reaction. Because when you're trying to estimate the sign of an entropy, make sure you focus on the gas phase species. They'll tend to dominate the system. However, there is a couple other special categories of reactions that is worth making note of. And one of the big ones that I want to talk about is going to be what happens when I dissolve a solid. So let's say I take good old sucrose, so sugar. Starts as a solid, I put it in water, it dissolves. Turns out that these sort of processes have very high entropies because I start with a nice ordered solid and a relatively ordered solvent, and everybody becomes very disordered. And as a result, these processes tend to be very nice. Some other processes that tend to really take advantage of this are going to be a lot of ionic systems. So, for example, table salt. We saw last semester that if you dissolve table salt, this is an actual endothermic reaction. It takes energy to break up a sodium chloride crystal. However, it turns out what makes this process go forward is that this has a lot of entropy going for it, because it turns out when I break apart sodium chloride into two separate aqueous ions, so not only am I changing phase, but I get double the amount. This is really powerful. However, I don't want you to think that all ionic systems tend to end up having a positive entropy, because there are some solutes, typically those that contain that release protons or hydroxides, that can actually organize the surrounding solvents. So if I try and dissolve calcium hydroxide, I release all of these hydroxide ions. And it turns out hydroxide ions really end up generating a nice ordered pattern of water around them. And this extra order added to the solvent can actually cause some very select categories of ionic solids to have a negative entropy of reaction. So this is actually something you should keep an eye out for. However, so far we've been figuring out how we can calculate entropies of reaction using the entropies of products and reactants. However, I haven't told you how to get those yet. So next time, we're going to try and figure out how we can calculate the entropy of a species. Until then, take care.